Hello, welcome to NCBS Neuro. This is lecture 6 about encoding and neural models. So suppose you were a neuron, and supposing that you had to tell the world how strongly you were activated. What kind of information can you pass on to other neurons? Well, the channel that you have for output is the axon. And what can you send along an axon? You can send action potentials along the axon. So something about the pattern of action potentials is what would encode the information that you want to convey. So today's lecture is about how neurons encode the information that they have accumulated through synaptic and other input, and how they transform this analog signal into the pattern of action potentials. We'll be spending most of our time on what is called an integrate and fire neuron as an example of a simple yet biophysically reasonable approximation to a neuron. And then we'll explore a few other neuronal models to see how they perform similar operations. So with that, let's get started. So I'm going to discuss the following sections. We'll discuss encoding by neurons as a general overview, the analog and digital aspects of it. We'll be spending a little time on what are called input-output curves. How does the output activity relate to what input is coming into the cell? Then we'll go down a list of neuronal models. We'll talk about artificial neural network units, not spend too much time on those. We'll spend quite a bit of time on integrate and fire neurons, because they do have some kind of biophysical basis. We'll spend just a little glimpse of what's called the drift diffusion model, and we'll have another glimpse of the Hodgkin-Huxley model, though we'll be spending far more time on that later in the course. And then we'll say hello briefly to Fitzhugh-Nagumo and Izikevich models. Okay, so with that, let's get started. So I've already run this past you very briefly, that there are multiple coding strategies that a network of neurons can employ. For example, you could have specific coding. If you have some feature space, you could have one specific neuron that responds to a particular kind of input. You can have distributed coding, where many neurons will respond to some extent to a range of inputs. And then you have the temporal codes, the codes that determine what output is to be conveyed by means of firing patterns. And that's what we're going to be looking at particularly today. So the simplest form of this is what is called rate coding, where the signal that you want to encode is simply proportional to the firing rate of the neurons. So supposing that we had this series of values that we wanted to encode, first a high value, then a medium value, then a low value. Well, you could encode it as a firing rate. So each of these little lines is an action potential. So lots of rapidly going action potentials to encode a high rate, a series of somewhat slower action potentials to encode the intermediate rate, and very, very slow action potentials to encode the low value. Now, there are limitations to doing things this way. First of all, you cannot have a negative firing rate. So that means that you can only encode things starting at level 0 and then going on up. But similarly, you can only have firing rates within a certain maximum range. And for most neurons, it completely maxes out at about 100 Hertz, usually much less than that. And then the third thing, which is a little bit more subtle, is that if you're looking at information by way of a firing rate, then you have to sample the firing rate for long enough to count enough action potentials to get an estimate. So in other words, you need to average the firing rate over some time. And that means that if you want to encode information this way, then there's a certain limitation in how fast you can do it. We'll come and see all of these things. Now, this form of rate coding, as we shall see, is the basic assumption underlying artificial neural network units, which don't even worry about action potentials. They just go straight from some input value, which is analog, to some output value, which is also analog, and we'll see that. The integrate and fire neurons, which we'll be spending more time on, do just this, and we'll see more of that. And one common place where such coding is often invoked, especially in models, is the visual system. There's something called interval coding, which says that the value is not an average firing rate, but it is the instantaneous interval between two spikes. So if you have two spikes which are very close together, then that implies that this is a strong signal. If the spikes are a little bit further apart, like this pair, then the value is a little bit lower. They're close together, it's high. They're quite far apart, it's low. They're very far apart, it's even lower. And finally, in the limit, if you just have a steady value, then they're at a uniform firing rate, and this then ends up looking a little bit like rate coding. So here every spike pair is conveying information, but there are limitations to this. So one thing is that the firing rate code was redundant. That means that it didn't matter very much if you lost one action potential. Here, suppose you lose, let's say, this action potential over here, the second one. Now your encoded interval is actually quite long from there to there, so you would completely misrepresent the signal value. Okay, so you lose information very rapidly with this kind of coding. And then you need some somewhat more sophisticated nonlinear mechanisms to decode this, but we'll see how those work. And as we saw over here, when you have a steady signal, this is just equivalent to a rate coding scheme. There's something still more involved called phase coding. I won't dwell on it. It basically has to say that the signal value depends on what time the action potentials come with respect to some underlying phase. So for here for example, these are close to the peak of the phase, so it encodes a high value. Here these inputs are close to the bottom of the phase, so it encodes a low value. We'll deal with this later. Okay, just to remind you, analog computation takes continuous inputs, it gives continuous outputs, and some biophysical principle such as Ohm's law can carry out analog computation. Here's an example. The resistor is carrying on the analog computation of converting the sum of two currents times the resistance into a voltage, and so it's doing both a summation operation and a multiplication operation. So let's move on then to digital versus analog encoding. So the key thing here is the presence of a threshold. If you have some kind of analog signal and you threshold it, then you end up with a digital signal, an all or none event. You can, of course, put in more resolution by putting in more bits, and we discussed that. But for our purposes, we'll be thinking mostly about a single threshold. Think about the action potential threshold in this context. So if you're above the threshold, then you fire. If you're below the threshold, you do not fire. There's another aspect, though, to encoding, which is the coding in time. So supposing that you can only sample at a finite rate, which is always true. So if you only sample at a low frequency, then you get only a few portions of the waveform, not a very good approximation. But if you were to sample at a higher frequency, you'd get a better picture of the waveform. And so this relates to how neurons encode things in time. Each action potential can be thought of as a kind of a sample of what the signal, what the activity, what the input was to that neuron at that instant in time. But the question is, well, how long is that instant in time? And so if you are a neuron that can fire rather rapidly, then you can encode a rapidly varying signal more effectively. The penalty that a neuron pays for rapid firing is, of course, much greater metabolic load. Therefore, neurons tend to optimize their firing rate to kind of match the frequency of the signal that they're trying to encode. Okay, so just to remind you, this is what the neuron has to do. You're familiar with this component of it, the Y-shaped neuron that we spent all this time looking at, different inputs coming at different times and different places along it, excitatory, inhibitory, and so on, and how they sum. But to remind you again, the inputs are digital, the computation in the middle is analog, and the output, again, is digital. And this is, again, precisely where the encoding thing happens. That is, you have to encode all of this analog activity in the pattern of firing of action potentials. So let's start looking at how this is done. The first pass on this is to look at what are called input-output curves, and the name is rather obvious, right? If you have some kind of an input, such as total synaptic input or some current that's coming into the cell, what is the output? Now, if your neuron was nothing but a resistor, then the total synaptic input times the resistor would give you a nice straight line, and it would look like this. It would be a nice linear input-output curve. Yeah? Of course, we're talking here firing rate. We're not talking voltage across a resistor, but you could imagine that a really, really simple, stupid kind of neuron could do this kind of conversion. Well, neurons are not quite that straightforward. The idea of this kind of coding is exactly what we discussed earlier in terms of rate coding. So you have some value, which is your input, and the output firing rate over here is just in some kind of proportion to that value. So a high value gives you a high firing rate, a low value gives you a low firing rate, and there are many kinds of values that you could encode. You could encode the brightness of a light, you could encode the pressure on your finger, or you could encode something quite abstract, which is how novel is a stimulus. Have you ever seen this before? And these can all be given some analog value and therefore in principle could be encoded as a firing rate. But there's something more to this, right? You already remember that a typical neuron has a certain threshold before it even starts to fire. Now, if that is the case, then obviously you're not going to start some firing rate at 0 input. You're going to have to cross the threshold for firing before you start firing, even if it is a perfectly linear output curve. Well, so this is the first elaboration. That is, there should be some kind of a threshold for firing. Now, it turns out that some neurons can actually fire spontaneously. So you could argue that they have a negative threshold for firing. We'll get to that much later. Typically, let's say that a neuron needs some kind of threshold activity before it starts firing, and that already shifts your curve to some degree. But there's another thing, right? I already indicated to you that neurons can't fire beyond a certain frequency. And the typical maximum firing rate for most neurons is of the order of 100 hertz. Some specialized neurons like Purkinje cells can go up to 200 or more hertz, right? So that puts a kind of a cap on the maximum firing rate. So your nice linear relationship is now only linear over a certain domain. There's a threshold, and then there's a maximum. Now, of course, real neurons aren't going to have these abrupt changes and totally linear things in the middle. What they probably will have is some kind of a more non-linear behavior where there's a gradual ramp up of firing. It increases in a kind of a linear way, and then it saturates out, but it doesn't saturate abruptly. It slowly maxes out. So this is a more typical input-output curve, right? Where your input is the synaptic input or the input current or some combination of other activity, and the output is what it is telling the rest of the world it is encoding. So with that general idea of what input-output curves are, let's just see how different kinds of models might implement input-output curves. We start with our artificial neural network units, ANNs, and see how they work. So we've already seen this briefly, but let's spend a little bit more time on it now. These are neurons that don't even bother to worry about the fact that neurons fire. These are very, very abstract models of neurons. And all they say is that you have some input, which is a firing rate. It's not a synaptic input. It's not based on a single action potential, but it's a firing rate. This firing rate is multiplied by a certain weight. Here's another input, another firing rate, another analog number, multiplied by another weight, and a third input, and so on, any number of inputs. So all of these weighted inputs are summed. That's fine. So far it's all linear, right? You have some analog value and you multiply it by another analog value and you sum the whole lot. So this is all nice and linear. And then what you do is you say, actually, you know, the output function of this, the input-output function we just saw over here, is some kind of a saturating function with a threshold kind of thing. And that gives us our output transformation, which is some nonlinear thing. And that is the output. Okay? But remember, this is analog all the way. Analog inputs representing rate, although there's no action potentials, it's just some number. The analog computation, an analog output transform to give you an output rate. It's still an analog number. It's not individual action potentials. So this is one of the simpler abstract models. But you can do an awful lot with these things. In fact, all the standard artificial neural networks do this. Here's a typical feed-forward artificial neural network. And these networks, as we shall see, can do things like convert the horrible, unpredictable, illogical spelling that English language rejoices in, convert that into a phonetic expression of the sound of the word. And that's what these kinds of little neural networks can do. Of course, now we have much bigger neural networks, such as Google and all these other big companies utilize to do this kind of a thing. And then you get into deep learning, which can do incredibly impressive things these days. They can be enormously complicated, 10 billion parameters, and all the big companies use them. And what are they? At heart, they are all of these very, very simple artificial neural network units with analog inputs and analog outputs. Anyway, we're not going there today, just to illustrate that you can do an awful lot even with these extraordinarily simplified units, which barely merit the name of neuron. Let's go to integrate and fire neurons now. These are considerably more biophysically based, and this is how they work. You take the equivalent circuit that applies to this, and you're totally familiar with this now, right? You have your capacitance, your membrane resistance and membrane battery, and you have your axial resistance. We'll ignore these. We'll treat this as a single compartment model, just to remind you, so we don't really need these. And now we put these, which you've already seen, your capacitance and resistance and membrane potential, and we add our synaptic input, which you've also seen. Okay, so far so good. This part of it you already recognize. This is standard biophysics. And then we add one more element, which is a thresholding operation, which does two things. The thresholding operation sends an action potential. So basically, every time the membrane potential crosses the threshold, it sends out an action potential. And the instant it sends out an action potential, it puts in a reset trigger. In other words, it shorts out the capacitor and it makes the charge across that zero. The membrane potential returns to that value, and then you have to start all over again. Okay, so this is the biophysics part of it, and this is the fire part of it. So here we are getting rid of the much more interesting stuff that happens in real neurons with voltage-gated ion channels. We just have a thresholding and a reset function. Okay, so this does linear integration of weighted inputs. It does thresholding and resetting. Let's see some of the properties of this. Yeah, what kind of input-output curve would you get with something like this? So let's think back a bit, right? You remember the analysis we had done for synaptic input. If you have widely spaced synaptic input, each of the synaptic inputs coming after a long interval is independent. The previous one is already over by the time the new one comes along. So you're not building up at all. But if your inputs come very close to one another in time, you end up with some kind of a build-up. It's a kind of a charging curve that you see. So now let's add to this the thresholding element and see what happens. So here it is. Our threshold is a line. It's a potential above which we say an action potential has been triggered. So here are the individual inputs. Nothing is happening. They are well below threshold. But with exactly the same threshold, if we give a series of inputs which are close together in time, the cell charges up, and sure enough, it crosses the threshold. Just keep in mind, something interesting is going to happen once this thing crosses the threshold. Hold that thought. First, let's just remind ourselves what this already does to the input-output curve. Since you need to cross a threshold, and since the threshold is not there immediately at a zero input, that means that we already have to be thinking of some kind of an offset for the input-output curve before it starts firing. But now let's ask what happens to the next spike. When does that happen? So here it is. You have charged it up. You've got multiple inputs coming together. It's crossed the threshold over there. And you've sent off an action potential. And you have reset it. The reset button has been pushed. And so now the potential of the cell has gone back down to resting potential. And so now you can imagine that you would charge it up again. What would happen? You charge it up again. That also in due course crosses threshold. It sends out an action potential and it resets, and so forth. So if you keep giving a steady frequency of inputs which is high enough to cross threshold, then at a steady rate you will keep crossing the action potential threshold. You'll keep firing at a steady rate. So a steady input here is converted into a steady output of action potentials. Okay, that's nice. What happens if you were to take this input and instead of giving it at this frequency, you gave it at a higher frequency? So input is stronger. Well, that's pretty obvious, right? Because the input is coming more rapidly, the cell charges up more quickly, it reaches threshold more quickly, and every time it does so, it fires an action potential, it resets, it charges up again, fires an action potential, resets, and you can see that the frequency of these threshold crossing events, of the spikes, becomes higher. The interval becomes smaller. So you end up with faster firing with stronger input. Well, that's very good. That's exactly what we wanted from our input-output curve. Yeah? Now, there's yet another thing to remember, which is that in pretty much all integrated fire neuron models, you add one more ingredient, which is, of course, very biophysically based. You say that there is a refractory period. Yeah? We'll see more of that in coming classes. But in this case, all that a refractory period means is that there's a maximum rate of firing. In other words, the cell saturates. And so you end up with an input-output curve that actually starts to look remarkably like the one that we had analyzed earlier. There's a threshold before it starts firing. There's a regime in which its firing rate increases as the synaptic input rate increases. And then eventually it hits a maximum firing rate. And all of this is coming from a very nicely biophysically motivated model. All of this is good standard cellular biophysics, and this reset and thresholding operation is the only kind of magic bit we put on top of it. Okay, so that's the integrated fire neuron. Let's look a little bit more at what this might mean if you had summation, if you had two different inputs coming into this integrated fire neuron. Yeah? So let's suppose here's our input spike train. Each of these lines is an action potential triggered by neuron A, by input A, and here's input B, and these are the action potentials that it triggers. Okay, so now I want you to, in your head, do the summation operation here. Yeah? You're going to think that you're an integrated fire neuron, and let's see what you come up with. Okay, so here's A's first action potential, the first action potential that this cell is seeing. So it charges up, but because there's a long interval to the next action potential, it just discharges. Yeah? And there's a threshold way up there. It's nowhere near that threshold. So nothing happens. Now you get an input at A and followed very quickly by two more inputs at B. So you charge it up, it starts to decay. You charge it up again because of now the input from B. It starts to decay. And then you charge it up again when the third input comes in. And because these three together are very close in time, you manage to cross the threshold. That's nice. So you fire an action potential here, you reset the potential, and then you sit around and wait. And you wait until the next action potential comes. It's on its own. It doesn't do very much. Now you have something different. Now you have B fire an action potential. After some slightly longer time, A fires, then A waits a bit, A fires again, then B fires again. Now, these are somewhat more widely spaced than this set of three, which came very, very close together. But because there's more of them, they charge up, they discharge, they charge, they discharge, and so on. But eventually, by the time the last one comes in over here, it crosses threshold and you get another action potential. And so on, right? So here is your output, right? So a neuron is analyzing these inputs, A and B, and what it's getting is, it's saying that here there is a burst of inputs, fire an action potential, sit around for a long while. Here there's a somewhat slower burst of inputs. So, okay, we'll fire another action potential, and so on. So what this neuron is doing here is actually something kind of clever. It's looking for something called coincidences. It's looking for clusters of action potentials. Yeah? A nice, long, slow, steady stream of inputs is not going to cross threshold. But let the inputs come close in time. Let them come in a burst, and that usually triggers an action potential. So this is, we'll see it later, this is what is called coincidence detection. It is looking for coincidence of multiple inputs coming very close in time. If you have to spread them out, then it takes a lot more inputs to pass the threshold. So this is more of integration over time. This is more of coincidence detection, where a lot of inputs come close together. So that is how an integrated fire neuron would do this computation of detecting what kinds of patterns there are in its inputs. Okay, I'm just going to give you now a very, very brief glimpse. This is called the drift diffusion model. So supposing you had an integrated fire neuron, and the inputs in this were very, very small, but the time course was very, very long. Okay, so it's two things. It's not just that the inputs are small, much below threshold, but it's also that they integrate over long periods. And so if you put in a lot of inputs over enough time, you will cross threshold. But there's something else happening here. You also have inhibitory inputs. So each excitatory input can be thought of as raising the potential of the cell a little bit. Let's follow this blue line over here, right? So here's where your cell starts. And here's the firing threshold. And what happens is The positive inputs cause it to go up, the negative inputs cause it to go down, and so it's something like a particle diffusing in undergoing Brownian motion. It's being buffeted by inputs that cause it to go up, other inputs that cause it to go down, and if you wait long enough between inputs, then it just drifts to some intermediate value somewhere in the middle. And so it's got a threshold up here, and it jiggles up and down, up and down, up and down. Oh, it almost got past threshold there because there's a sequence of positive inputs, but maybe there was some negative input shortly after, so it came down. And so it bounces up and down very much like Brownian motion. That's why it's called drift diffusion model. And finally, enough excitatory inputs come in, few enough inhibitory inputs come in, and it crosses threshold, right? And so you can imagine that in this particular case, it took a long time to get a spike, but here you had a burst of inputs coming in, excitatory inputs coming in. That's what we saw with the integrate and fire neuron. If a burst comes in, it'll cross threshold quite quickly. If, on the other hand, a bunch of negative inputs comes in, the cell will just sit at the bottom response. The upper response boundary is the threshold for firing, you can imagine, and this is just the minimum potential that the cell reaches. So this is the drift diffusion model, and the reason why this is interesting is that you can think of it as allowing a cell to do decision making based on accumulated evidence over time. So let's suppose that the positive excitatory inputs were signals to say that yes, I should make a certain movement. But the negative ones were signals that said, no, I should not make a certain movement. And so you keep getting these signals coming in, and it's only when there's enough of them that cross the threshold that you actually decide to make the movement. Accumulated evidence. Yeah. So that's the drift diffusion model. Let's now very rapidly go through three kinds of more sophisticated models. Let's start, of course, with the classic Hodgkin and Huxley model based on the ion channels that were described by Hodgkin and Huxley. You have a cell which receives a stimulus. At some point, it causes the potential to rise, and that causes opening of ion channels. The ion channels, sodium channels open. Eventually, the potassium channels start to open and reverse the depolarization, and it comes down, and you're ready for another action potential. This is a system that has a threshold, and it has many of the characteristics much more biologically realistically than does the standard integrate and fire neuron. And the way this is implemented, and we'll see more of this later, is that you have ion channels which are again variable, similar to your synaptic channels, except that these are now voltage gated channels. We'll see much more about this. But the key thing about this is that this too has a threshold. So in combination, these ion channels do both things that an integrate and fire neuron does. It sets a threshold, and after the threshold, so there's a threshold somewhere over there, and after the threshold, the cell's potential is reset. Both of these are things that the integrate and fire neuron does. And of course, the integrate and fire neuron was modeled after precisely this, after the real neuron's action potentials. So the I/O curve for a Hodgkin-Huxley model is actually quite similar to what we've seen. This is not a real I/O curve, this is just a sketch, but there's a threshold, there's a buildup of firing rate, and there's a saturation rate because it has a refractory period. So very similar input-output curves. We'll see a lot more of the Hodgkin-Huxley model later, but let me just introduce you to the Fitzhugh-Nagumo model. And this is kind of a cool model. It was independently developed by Fitzhugh over here and a Japanese neuroscientist, Nagumo, who actually implemented it in silicon many years ago. The equations that define this are as follows. dV by dt is some complicated cubic term of voltage, and dW by dt, which is W is some magic internal value, is this other magical equation. And you put these things together, and what you get is a system which oscillates when the inputs are sufficiently strong. Okay, so this doesn't look at all really like an action potential, and I totally agree with you. It's not really looking like an action potential. The reason why this was so influential in the field was that it does one thing qualitatively the same as neurons do, and that is that if you give it an input, if you add to the value of W, for example, or V, you can cause this to go from a threshold below which they're not oscillating at all. Above that, they start to oscillate in a periodic way. You give it a stronger input, they oscillate even faster. So although these things don't look a lot like action potentials, they do have some of the key qualitative properties. And the reason why these were studied so much is because this is a very nice simple of equations. It made the mathematicians very, very happy. They were able to bring a whole lot of powerful analytic techniques to bear and ask what might happen if you have a system which obeys the Fitzhugh-Nagumo equations, where an input can cause oscillations, and the oscillations rate can be modulated by the strength of the input. And so they spent a lot of time analyzing this, hence the value of the Fitzhugh-Nagumo equations. So again, we come back to the point of coding, right? These, not really neurons, these equations were encoding the strength of input in a firing rate. Finally, we come to some much more modern version of an abstract model. This is due to Eugene Izikevich. And so he too came up with a really remarkably simple set of equations that look like this. The reason why this is such a remarkable set of equations is that these are the outputs that you get depending on the parameter range. In all cases, here is your input current, and this is your output potential. And the remarkable thing about these equations is that it generates output potentials, quote-unquote potentials, that look amazingly like real neurons. In fact, they look like a lot of the complicated firing properties of real neurons, most of which you haven't even seen yet. So here are regular spiking neurons. You give it a stimulus, they fire it in a periodic way. This is simple coding. But this was a different kind of neuron. Real neurons do this too, by the way, many of them, where at the initiation of the step of current, they fire a burst, and then they settle down into steady firing rate. Here's another very interesting and a fairly common form, which is that you give a step of input, they fire a burst, then they go silent. They fire another burst, then they go silent. So if you were recording from this and putting it in your earphones, you'd hear prrr, prrr, prrr. That would be the activity, bursting activity of this neuron. You can have fast spiking. You can have adapting. So it starts out firing quickly and then it slows down. You can have other neurons which fire in a burst and then they're silent altogether. You can have other kinds which sit around for a while and then finally start firing if you give them a little pulse. And then you have low threshold. The value of this kind of a model is that you can then make large network models which actually have firing properties similar to real neurons, hence the coding. Okay, so just to reiterate, this whole lecture has been about how neurons do coding. And we've seen a range of coding properties for a range of neurons, starting with the very simplistic, abstract ones that are used in artificial neural networks, the integrate and fire ones. We spent a little time thinking about the implications of this for drift diffusion model. And then we looked at the more realistic biophysical one, which we'll spend a lot more time on, the Hodgkin-Huxley, Fitzhugh-Nagumo, and Izikevich types of models. Yeah? Just to remind you, take-home message. You can do rate coding, and this is quite easy to do with neurons. And in rate coding, what you have to do is you have to convert some input value into an output firing rate. You've seen this through input-output curves, which define how a given value of input gives rise to a certain output firing rate. You've seen this happen in different kinds of neuronal models, artificial neural networks, integrate and fire, and we'll come to the implementation of this in networks in due course. You've just had a little glimpse of what you can do with interval coding, where maybe two very close by inputs can be representing a strong stimulus, and two somewhat more distant inputs can represent a weaker input. And you've seen then how neurons can encode all of these through different mechanisms, especially with reference to the biophysical basis of the integrate and fire neuron. With that, we end this lecture, and I just want you to remember, think about it from the point of view of the neuron. How are you going to represent the various inputs, the many kinds of inputs that are coming to all your branches? How are you going to convey this information to the rest of the world? And what we've done in this lecture has been to ask how different kinds of neuronal models achieve this, from the very, very simple ones to the biophysically based integrate and fire ones, the really biophysically based ones, and some other abstract forms. But they're all doing the same thing. They're taking inputs and they're figuring out how to tell other neurons downstream what was the value of all that activity, what do I want to tell the other parts of the network. So hold that thought and see you in the next class.